Okay, so we're going to continue from last time, now looking at textures in more detail. So I've taken the 3D model things out for a moment. If we have time, we'll look at actually texture mapping more complex objects. But to begin with, we're just going to look at how the textures work, how we can get them to work with our shaders. We're going to set up and learn how to use the UV coordinates and set up a little UV map for a cube, and see if we can do a spherical map as well and some more complex stuff. So the question is we need to look at how the UV map itself works. And so we can work with that, or we can start by well, there are two things we need to do. Set up the UV map and make sure that we understand how the coordinates in the UV map work and how they're connected to one another. And the other thing we need to do is to actually find a way to talk to the texture itself, or the texture image in our shader, and find a way to sample the correct color from the correct position in our texture image for every single pixel that we write out. So to begin with, I've already set this up, so I'm just gonna add shading here. Add textures to this single cube here. So the way I've set this up is I simply have a texture that I read. You can see this is a libgdx specific class here that's called texture. And we're just going to use this one first. Texture here, and the simplest way to use it is simply to instantiate it using a file handle, and it'll read pretty much any PNG image and most JPEG images into a texture. So we'll look at how the texture actually gets read in later on, but for now we have this texture here, and we can just look at what it looks like. And the way I've built the box graphic here is when I call draw solid cube, I call it with a couple of textures that I've already loaded. So we're going to ignore the second one and just imagine that we have a single texture, that is just the color texture, rather than splitting it up into diffuse and specular. We'll look at the specific diffuse and specular texture, and even opacity or like transparency textures and shininess texture. Basically any value that we want we can set in a texture and set up that way. So the material is kind of our base color, but the texture is a more kind of detailed color image that we're gonna kind of wrap around the object that we're drawing. But to begin with, just to get something here, I am going to just take text here, go down into where I call this, and rather than saying null here, I'm going to say text. So that should display some image here. Okay, so now we have an image that's being drawn, the same image on each side of this cube, and you can see that the specularity is happening afterwards in this case. So we're using the fragment lighting shader here, and there are a couple of things happening there. We're gonna later on set the same thing up for the vertex lighting shader, see how it works, get it to work there, and then go back to the fragment shader and set this up a little bit more complicated. But for now we can see that you can see that the pink color isn't there anymore. So there are two ways of looking at a texture, or a color texture like this. One of them is what I'm doing here, which is simply saying that if I'm using a diffuse texture, I'm going to set the diffuse to what I get out of the texture only. If I'm not using a texture, I'm going to use the material. The other way to do this, which is the way it's done in a fixed pipeline, is to say the material I have is kind of a base color to everything. So I'm actually going to say I use the material, the base material of the object that I'm drawing, and I multiply that with the texture. So both are having an effect. And the difference between this would be like so. Okay. So let's go to a place where the specularity isn't as obvious. So now I can see, we see the image there. We also see that kind of pink purplish color that was there, and they're simply multiplied together. So we're taking the material and we're adding the texture onto it. The more colors that we take and multiply together, the darker overall our image is going to end up, because everything is attenuation. We can never have a value higher than 1. 1, 1, 1 will give us white, and 1 will give us full intensity for any color. So every time we're taking a number between 0 and 1 and multiplying with another number between 0 and 1, we're always kind of pulling the color down. So usually when you're using textures, and it's done in this way, where you're taking the base material and multiplying it with the texture color, usually you end up simply using the material that's fully white, just 1, 1, 1. And if you can say, in my program, I'm always going to do that. When I'm using a texture, I'm simply going to set the material to 1 and ignore any underlying material. And it's just as simple to say, well, I'm simply going to replace the diffuse material with the texture if I'm using a texture. In this case, we're using a texture, and so it's the texture only. In the case where I set this to null, and I just set up code inside the draw solid cube that says if this is null, then I tell the shader not to use textures. If it's not null, then I tell it to use this texture. So now it'll end up using the material instead. So here we're using material only, and here we're using the texture only. We'll look at how this works, that is actually getting the texture data to work. But I'm going to look at the UV coordinates first. So now that we just have a little handle on what we're doing, we're taking this cube and we're stretching this texture image onto the polygons of the cube. Then I'm going to look at the UV coordinates a bit, because they're kind of a nice and simple way to get into the idea of how the textures work. And we'll look at actual color sampling later on. So this is the image we're going for here. But obviously, we're just taking the same image there, and also the image I'm using here is a spherical map of the moon Phobos of Mars, so that doesn't really belong on each side of a cube. So we're going to take something else now, but to begin with, we're going to look at box graphic here, and ignore for a while how we're talking to the shader, and just look at these arrays. So last time we looked at this change here, where we're using the index array rather than just reading linearly through the vertex array and normal array. But in the end, the vertex array and the normal array simply have 3 and 3 numbers together, each representing either the vertex itself in the vertex array or the normal for that vertex, and they're always indexed together. So anytime OpenGL wants to use vertex number 5, it'll use this vertex, or no, 0, 1, 2, 3, 4, this vertex. And when it sends it into the shader, it'll send along with it this normal. So that's the data that will always be used together in the normal, because it's in the same place in these arrays. And so we're going to make a third array, or a third buffer, called the texture coordinate array, or the UV buffer. And the UV buffer has 2 and 2 numbers together. And we can see when we're actually telling OpenGL to use it as an attribute pointer, that we tell it to take 2 and 2 numbers together when it sends it into OpenGL. So OpenGL, like this, the way we're using it with the shaders, it doesn't kind of implicitly set one meaning or another to specific arrays. We have a vertex array and we have a normal array and a UV array, which is a very, very common way of using these. But the shader itself doesn't care what we're sending in. We're just saying we have a list of numbers here, and I want you to take 2 and 2 of them together, or 3 or 3, or 4 and 4 of them together, and I want to be able to work with them in that way in the shader. But you can basically send any data that you want in this way. For now, however, we're sending this UV pointer here, or this UV buffer, and we're asking OpenGL to read 2 and 2 numbers together. So after we've set this up, it'll go to the vertex buffer and take 3 numbers and send that into basically the location of the shader that the vertex pointer points to. It'll take the normal buffer and send it to here, and it'll take numbers from the UV buffer and send them to where this is pointing to, and it'll take them 2 and 2 together. So in the end, again, if we're using vertex number 6 or vertex number 5, it'll take these numbers here and send them along with it. The way we use these numbers is simply that see if we have room here that I haven't already. Okay. So okay, the way we use this is that we imagine that we have a texture image here, and that's just some picture that we can read, and it's a rasterized image, so it's a pixel-based image. But the coordinate system that we use to read from it has the u coordinates here and the v coordinates here. They could just as well be x and y, doesn't matter. They have 1 exactly here, and they have 1 exactly here. So this is the coordinate system that we use to index into basically positions on the texture. So what we're doing on the cube is we have this 3-dimensional cube here, and what we're saying is when we send this vertex here in, we want these coordinates from the UV map to be sent along with it. When we send in this vertex, we want, when it's part of that is this this polygon, we want this coordinate here. So 0, 0 on the UV map goes along with this vertex. 0, 1 goes along with this vertex. 1, 1 goes along with this vertex, and 1, 0 goes along with this vertex. So we're telling OpenGL to map basically this corner to this corner, this to this, this to this, and this to this. And when we go from the vertex shader to the fragment shader, we want the interpolation to end up sending basically any location within the texture, whatever location it is, to the right pixel or right area on the image that we're drawing. So for any pixel that will be drawn as part of this polygon here, we're basically interpolating through this, and any pixel here will have some interpolated UV coordinate. So some pixel here will get an interpolated UV coordinate, something like 02506 would be this location here, and those interpolated UV coordinates will give us the position within the image that is supposed to be set to this. So it basically goes into the image and says, at this location in this coordinate frame here from 0 to 1 on each side in these UV coordinates, what is the color of these UV coordinates? Are there any questions here? Is this clear, or do you want me to start again and try to explain it in different terms?
Is what clear?
The idea of how we're indexing into the texture in 2 dimensions. So we have these three-dimensional coordinates for the basically for the vertices. But what we save for the vertex, if we go in here again, what we save for the vertex in the vertex shader are either, if we're doing vertex lighting, we just save a color and then we send that on. And in the fragment shader we get an interpolated color depending on where basically in the pixel space between these vertices this particular pixel is, and we get the same interpolation for the UV coordinates.
So what if the area we're trying to put the texture on is like way bigger? Doesn't matter?
No, it doesn't really matter. I can actually show you that. If we take, I think I have some weird texture image here. Okay, let's just look at what we have here in textures. I think this spec text here is tiny. Or no, this text 01 is probably a very small image. So let's just go in here and say we're gonna, okay, it's a weird image, but it doesn't matter. Okay, so I can simply go in closer and you can just see the pixels. So the pixel, each pixel in the image in this case, you can see those white spots, which are just single pixels. You can make it stop moving. I think that'd be nicer. Okay, so we can just take the rotation out here and just make it stand still. Okay, so I'm going to go up close and you can see how this pixel here, actually there's some kind of averaging going on there, but the idea is that the color from this pixel here is ending up in many pixels in my rendered image here. So if the texture is much smaller, then at any point that I'm sampling into it, you can imagine in here, if this is a very tiny image that's like 8 by 8 or something like that, and like so. Okay, let's imagine this is just one pixel, and then I have a fairly high resolution three-dimensional thing that I'm rendering this onto, and so I have a tiny pixel that's here, and it just says for the coordinates in here what will be the texture coordinate, and I simply go here and this is the color I'll get. Then I go to the next pixel, which is right beside it, and it asks for the color for this UV coordinate, and I'll go in here and I'll just get the same color because it's still within the same pixel in this image, even though it's a different pixel here. So pixel to pixel there is no kind of correlation from pixels in the texture to pixels on your screen. And the other way around, if I just go way back, okay, now obviously this image is covering fewer pixels in my rendered 3D image than there are actual pixels there, and then just some of the colors will be skipped. So let's imagine the 3D image now is tiny, and so there's just one pixel that covers all this space. I'll just ask for a sample and it'll just give me one of the pixels that covers it. So yeah, it's simply I'm interpolating the UV coordinates, then I sample the texture with those UV coordinates. So it's two parts. It's the interpolation of the UV coordinates, and if we ignore that for a while and just say once I have some UV coordinates, I simply ask OpenGL or the texture or my texture to sample this UV coordinate in the texture. And so if I have a UV coordinate 0.3 and 0.6, that'll be somewhere around here and somewhere around here. So simply the closest pixel will be the color I get. But you can ask OpenGL also to sample in different ways. You can tell it to sample closest pixel, which means you'll get the full color of the pixel that's closest to those UV coordinates, and the same color until you get another one. Then you'll get a really pixelated image. You can ask it to give you an average. So if the UV coordinate sample is somewhere around here, it'll say, okay, I'll take most of this color, but a little of this color and a little of this color. Basically calculate between the colors that are close to that. And that's basically what's happening in our case here, because you can see that it's taking a little bit of an average here into some of the pixels. Or no, it's probably not. No, it's definitely closest here. When we go this close, we can see it. This is just the way the image looks. Okay, so sampling into it. Is this idea fairly clear? The main thing is, what are we mapping to the corners? And for now, what we're actually mapping here is we're saying for the first polygon, which has these 4 vertices, or it's actually the first polygon has these 3 vertices, the next one has this vertex and these 2 vertices. So it's 2 triangles, but let's look at it like a quad. So the first quad, the first side, has these 4 corners, and if we go to the normals, no, sorry, it has these 4 vertices. If we go to the normals, those corners all have the same normal because it's all facing the same direction. And finally, those 4 vertices will have these UV coordinates: 0, 0, 1, 0, 1, 1, and 0, 1. Basically, the very corners of the texture, meaning that when we map this, we're mapping the entire texture to a single side. The next vertex, no, sorry, the next quad, the next 4 vertices, they just have the same texture coordinates, the same UV coordinates: 0, 0, 1, 0, 1, 1, 0, 1. So we're just repeating this all the way down: 0, 0, 1, 0, 1, 1, 0, 1. So we're taking each of the sides of the 3-dimensional cube and we're mapping the entire texture onto it. Alright, but we want to do something more interesting. So what you can do is just go somewhere and say dice texture or whatever kind of texture you want. Image search, and I think it's this one that I finally took. It's nice to look here at the resolution. If the resolution only has numbers that are whole powers of 2, basically 128, 256, 512, 1024, then they're probably designed as textures for 3-dimensional imaging. So those are the nice ones to take. I'm not sure about libgdx, if you have to do something special to read other sizes of textures in, but I would strongly recommend only using whole powers of 2 on each side. They don't have to be evenly sided, they can be 2048 by 1024, but using whole powers of 2 simply because the texture sampling is immensely much faster if it has textures like that. If you force it to have other sizes of textures, the algorithm that samples will suddenly become slower because it can just use kind of binary search type methods to sample into it if it has these whole powers of 2. And usually OpenGL implementations will simply force you to do that and just not read a texture that's set in another way. So if libgdx allows the other one, they're probably upsampling them to the next whole power of 2. Anyway, so I took this one and I stuck it in here. So we have this. No, okay. It's not going to help to open it here. Anyway, let's just look at it in the browser then. Okay, so this is the image that we're looking at. So if we now want to change our UV coordinates so that we'll get one side of this on each side. So I mean, one way to do this would obviously be to have 6 different texture images. One texture image for each side and setting a different texture for each side of the cube. But in that case, we'd have to draw each side of the cube separately as well. Do you understand? Because we'd have to bind a new texture for each side that we draw. But if we want to keep our current index array here that draws the entire cube in one go, and our current draw solid cube function here that simply sets the shader's vertexes, normals, and UV coordinates as vertex lists, and then simply calls draw elements. We need to set our UV coordinates so that it can take this texture image and set each part of it, each side of the die to each side of our texture.
So you can split these into like 9 rectangles?
Yeah. So this is basically 9 rectangles, except 3 of them are empty and we're not going to use them, so we're going to use 6 of these. So we have basically each side of our 3-dimensional cube will have a 9th of the whole texture image put onto it. So let's just see if we can do that together. How can we change this UV array so it'll do exactly that? We start just by getting one side right and see if we can do that.
Yeah, so go from 0.25.
Are you sure?
33, yeah.
Yeah.
That's 3, of course.
Okay, which side are we going to grab? Let's just look at this and decide which one we're going to take.
Take this 3, or do we take 1 first? That's simple.
Yeah, we can take the 1. That's okay. We'll see. If we take the 1, we won't actually see if we're counting kind of from the right side. You can sometimes have trouble actually understanding exactly how libgdx read the texture in if you're reading it from this side, or from the top, or from the bottom. But let's start with the 1, because we're pretty sure that'll work. So the 1 is in the center. The center 9th. So we're going to start at 0, 3, 3. Okay? So before we were going from 0, 0 to 1, 0, or 1, 0, since I'm facing you. What would then be the number here? So now we have this. Instead of 0, 0, we're now doing 0.33, 0.33. What should be the coordinate of this point here? 0.66 on the x, and what on the y? Okay. Next one. Are you sure? We were at 1, 1.
Oh yeah, okay.
Yeah. Yeah. And the last one would be 0.66 here and 33 here. Okay, let's see how this looks. Ah yeah, we haven't changed the texture image. But we are taking the center from it, right? Looks like it. So let's go back in here and just change the texture image. Dice. Can you see what's happening here? Specularity is... Okay, so now we have the full image spread onto all of the sides, except for this one side, which has the 1. So we might actually take the specularity down a bit. So where are we actually drawing this? Here, specular. Let's just set the specular to 0. Oh, we have that there. Okay, so the 1 turned out nicely. So let's look at what the next coordinates are here. Or just look at the normals, that's actually nice. So this should be the side opposite the side we just did. So what we're going to put there? Okay, put the 6 there. The 6 is down here. Now we're going to find out if we're actually counting from. I believe we're counting from this corner. So let's try that. If we get something other than the 6, then we're going to have to change it around. So what are the coordinates going to be now? Okay, 666 on x. 0 on the y, yeah.
It's 2, 1 there.
So here's a 1.
No, that's the 066 and the 1 in the right?
066 is what we're going to do on the x coordinate. But y, it depends on whether we're counting from above or from below. I'm going to believe now that we're counting from below.
Wait, in what order are we taking the coordinates? This order.
Yeah, we're going to do 1, we're going to do 6 now.
Yeah, I know, but...
Oh yeah, this corner, this corner,
Oh, okay.
this corner, and this corner. That's the way they were, right? They were 0, 0, then 1, 0. It doesn't matter though. We can do it in any order, and just since they're done here, always 0, 0, 1, 0. So we're working on the x first, then to the xy, and then finally at the y. So if we do it the same order, 0, 6, 6, and 0, then we're going to 1.
This doesn't change.
This doesn't change, yeah. Then we're at 1 in the x,
And 0.3.
0.33 here. And finally,
0.66
go back to 0.66 here.
and 0.66.
Okay. Let's see if we nail the 6 here. Nope. Okay, then we kind of have to figure out. Okay, we can see it actually here, how it's being mapped. So we're counting from above. So it's the y coordinates we need to change. So okay, how can we change the y coordinates?
So 0.33 becomes 0.
Does it?
0 becomes 1.
0.3 becomes 1, I guess. And 0 becomes 0.6. Like so. And were we here? Yeah. Okay, so the texture coordinates we're counting from the other side, or from the top. So now we have a 6. It doesn't actually turn the way we thought it would be, but let's not worry about that. If you're very particular in the textures you're doing, you have to consider this better. But all right, so let's do the rest, just all in one go. No, not gonna. Okay, so now we have the side facing up. I just know that 2 is opposite to 5. I don't know exactly how a perfect die is supposed to be. Let's just do 2 now. So 2 is here, and since it's in the center, it doesn't matter with the y. So okay, the x coordinates will now be 0 and 0.3, right? And the y coordinates will be 0.3 and 0.6. 0.6. No, I could do. I'm just making sure that it's. If we want to make it super close, we just actually do 1 divided by 3 and 2 divided by 3. No, I'm just. Obviously, it'd be close enough even if we just had 1. Okay, so there's the 2. Now let's do the 5. 5 is right on the other side from that. So we could probably just take this, paste it over here, and say we need to change the x to 0.6 and 1. And 1 and 0.6. Okay, that should give us the 5. Then the 3, well, the 3 and 4, yeah, it doesn't matter which one we do first. They're both in the center on the y, so they'll both be 0.33 and 0.6 on the x, right? We have something else that's like that here. Take it like this, that, and then we have to change the y. One of the y's will be 0 and 0.3, and the other one will be 0.6 and 1. I wonder if it matters in which order we do it like this. Since it's a die, it doesn't matter so much if things are upside down or not. So we have a 4 here, we have a 6 here, we have a 3 opposite the 4, and we have a 5 here, and a 2 opposite the 5.
Look at the 5 again, it's kind of
Did I? Here, yeah. But just on one of them. Okay. It's not skewed like it was, but it's a bit off. So is that just the texture image that isn't? Let's see what I'm doing with the numbers there. 1, 2, 3, 4, 0, 6, 6, 0, 3, 1, 0, 3, 1, 0, 6. Yeah, and then 0, 6, 0, 6. I don't know, if we look at the texture image, isn't the 5 just a little bit too close to the edge here?
Yeah,
It must be something like that.
that's wider from the two.
Yeah, it seems. At least let's not worry too much about that. So, rather than going into the UV coordinates and making them perfect, I just send this image back to the artist and say, give me a better dice texture. That's exactly in the center of the thirds. This is good enough, and this is the idea. You don't have to spend more time on this. So this is the idea of texture mapping. So we're simply saying each vertex in the three-dimensional object is mapped to a two-dimensional coordinate in the image, and depending on which UV coordinates each vertex in these three-dimensional polygons is mapped, we'll get some interpolation that then samples into the image and basically stretches it over. So the idea is we're just sampling into specific locations in our texture, and then those are being stretched over the entire polygon that we're rendering each time. Are there any questions about this in this kind of simple cubic cube map of the die? Are we on the same page with how at least this works and how these numbers are talking together?
Can I see the mapping code again?
Yeah. So the mapping itself is simply just in the UV vertex list, or the UV coordinate list here. And for each index into this list, this is the UV coordinate mapped into the vertex at the same index in the vertex list, and the normal at the same index in the normal list. This is the mapping itself. How we send the mapping is just the same way as we send the vertex pointers. We just tell OpenGL, here is some buffer, and there is some variable in my shader that I want each of the elements from this buffer to be read into every time the main function is called. So OpenGL runs through these buffers in parallel and just takes the numbers from each of them, sends into the correct variable in the shader, and calls the shader's main function. Then if there are more vertices in the list, it goes to the next index and takes that vertex, that normal, and that UV coordinate, and sends those together into the shader. So if we go into the shader itself, no, that would be the vertex shader. Shaders here, fragment lighting, vertex. Here, what we have here is we just added an attribute. We had the attribute position. We've always had that. We've added the attribute for the normal and the attribute for the UV. So because of how we ask this to be read in, we make a vector 3 for the position, a vector 3 for the normal, a vector 2 for the UVs, and we know that it just runs through the list, makes one of each of these, and then calls this main function. And so we can use these variables knowing that they're coming from these lists together, and we can work them out. The only thing I'm doing with the UV coordinates here is setting them to another coordinate. That, however, is a varying coordinate here. So I'm taking the UV coordinates for the vertex, I'm sending them into the varying coordinate for the UV, and then I just trust that the rasterization process of OpenGL will interpolate that for me, because I can only use it in the fragment shader. Even if I'm doing vertex lighting, I have to use the texture in the fragment shader, because otherwise I just get one texture location or one texture sample for each vertex, and that would really not give me much. So in the fragment shader in this case, I get this varying UV here, and I use it here in this function. There's a function in the shader called texture2d, and it takes some variable of the type sampler2d, which is simply it's kind of a pointer to where this texture is bound. I'm not actually sending the entire texture data into the shader, I'm just sending it kind of a handle to a texture. And so it will call OpenGL with this texture2D function here, with this sampler and this coordinate, and say the texture behind this sampler here, what color will that give me at this coordinate? And then that's what I get returned. And that's put in this case into a vector4, which is basically a red, green, blue, alpha color. And yeah, this is just something I was experimenting with here. You don't really need to do it this way. This would be a much better and simpler way to do this. Just material diffuse equals this. And again, if we say we want the base color to affect this, so we want to be able to use this same texture, dice texture, but to draw multiple colored dice. We can do this way. And so we have a single dice texture, where we could now draw multiple instances of this cube using the same texture, but giving it different materials and thus getting different colors. So yellow dye, pink dye. So in some cases you want to use the two together. In some cases, however, you just want the texture to be the texture. Okay, so what I want to do now is to actually switch back to the vertex lighting shaders and just build this up from scratch, build this texture functionality up from scratch into them, and then we'll look at how it looks in the fragment lighting type shaders. So to begin with, I'm going to go into the shader class. And if you're using different shaders a lot, it's probably nice to just build separate shader classes, especially once the shaders start using very much kind of different variables. It's not a huge deal if you actually try to get a position, a location for a variable that doesn't exist. OpenGL doesn't complain, and if you try to put data into something that doesn't exist, it's okay as well. But as soon as you try to set up an attribute that doesn't exist, then it'll probably crash shader. But obviously a variable that doesn't exist doesn't do anything special. So I'm going to go here and go into the vertex lighting shader. We'll probably get a crash the first time here, and it'll tell us that in here we were trying to set this attribute pointer for the UV coordinates, and since we don't have any UV coordinates yet, it's normal that nothing should be happening. Okay, so now we simply have the material here, and we're working, as you can see now, with the vertex lighting. So the lighting isn't as pretty as it was earlier, and here's this. Sorry, yeah, we can kind of see the polygons because we calculate the light only in the corner. So we calculate the color here and here and here, and then it's just interpolated the color itself. Whereas in the other case, we calculate normals and directions, then interpolate them, and then actually calculate the lighting and color itself for each pixel. But never mind that. So now we're working with that. We'll just be looking for now at this cube here. And just to make sure that the material doesn't matter at all, let's just set that now to 111, meaning that the color we see is just the pure intensity coming from the diffuse shading. Okay, so this is just pure here, and we'll just add that on. So if we go into the shaders themselves, now we're using the vertex lighting vertex shader, the vertex lighting fragment shader here. Okay, we need to add something here. To begin with, we need to add this attribute for the UV coordinates themselves. So we can start with that, a UV, have that a vector2. We have to make sure that these things fit in the attributes, otherwise OpenGL will not understand exactly what we're doing. It's not a big deal to have variables that we don't use, or variables that we try to access but aren't there. But as soon as we actually try to kind of use them or calculate with them or send vertices into them, we'll get a bigger problem. Anyway, so this is very simple here. We're doing the lighting here in the vertex shader, and we end up with the GL position here, and we end up with the V color. Those are basically the output variables here. And so since we have the V color here, I'm going to say the V underscore UV equals the attribute UV. Okay, so this is the only thing we do to the UV coordinates in the vertex shader. And it seems like we're not doing anything, that we're just taking the numbers that we put in, putting them into another variable, and then going ahead and using that variable here. But as you remember, or as it would be good to remember, then even though we're using the same variable name here with a varying, we know that the version of it that we end up with in the fragment shader is the interpolated version, the interpolated value for each pixel. So we're using it as the same variable or as the same name. We have to know that the main function for the fragment shader is called for every single pixel that the polygon that we're drawing now is rendered onto, whereas the main function for the vertex shader is called once for each vertex. So this is going to be called a lot more times, and this will be an interpolated value. Okay, so what we're getting here is the color, the interpolated color, and the interpolated UV coordinates. So what we're going to need here as well, and we might as well just steal that from here. It would be nice to have actually this. So a variable here that I'm using to ask. The reason I use a floating point here rather than a boolean or an int is just because in some cases older versions of the shader language or shader language implemented for phones and handheld devices will only accept kind of one type of variable, only accept floating points and not handle integers, just to make the hardware simpler. But no, there's no big deal with that. So I'm using a floating point here, just saying if it's 1 then it's a true, otherwise it's false. And I'm using this sampler here for the diffuse texture. So I'm adding the sampler, and that's the main thing. The uses here isn't such a big deal, but it's nice to have it just to be able to switch on and off textures if you want to render one object with the textures and another one without. So now I have these variables, and what I basically want to do then is to say if just copy this here, uses texture, and for now you could actually ignore this diffuse idea. We're just using this as our entire texture. We're taking the entire color with specularity and diffuse and all the calculations that happen in the vertex shader, and we're simply multiplying that with the shading, with the texture color, because we don't have any split here in the fragment shader. We just have one color. If we want to have a separate diffuse texture and specular texture, we're going to have to also have a separate varying diffuse color and varying specular color. Alright, so if it uses the diffuse texture, if this equals 1, then we want to do one thing, otherwise something else. So if it's not using the diffuse texture, we simply want this to be the color. If it is using the texture, we want this to be the color times, let's steal this from here as well, so times the color that we get by sampling this texture at this coordinate. So we're simply taking the color we get from the vertex shader and we're multiplying it with the texture color that we get. Let's see. what happens now? Let's go into the shader as well. So what we now need in the shader, obviously, are locations here for the uses diffuse texture. Well, I'm setting a specific boolean here. This is the location, and this is the diffuse texture location. Okay, we're getting variables for that, obviously, the usual way. And then I have this function here called set diffuse texture, and I just use this class texture here, and I say if I send null into this, then the shader itself will say, then I'm going to set uses diffuse texture location to 0, meaning that it won't use the texture, and then it doesn't really need to set the texture to anything. It just says I'm not going to use textures now. Whatever texture I used last will just lie in memory, but it doesn't matter because I might want to use that again later on, because I'm switching between textures while I'm running each frame, but all the textures I use will simply stay in memory and wait to be used at any time that they need using. Otherwise, if there's something in here, I call texture.bind, and behind this bind function here on the libgdx texture class, there are a couple of OpenGL calls, but the idea is that what happens in there is that we simply tell OpenGL, here is an ID to a texture, and the texture class here simply stores that ID. But it says, it takes that ID and says, I want you to basically bind this particular texture as the current texture in this texture location. So I have basically, I can use several textures at once, and I'm using the location 0. I'm saying the first texture should be this diffuse texture that I'm going to use. So I bind this texture in OpenGL. So from now on, whenever I use a texture, this is the texture that OpenGL will use. Whenever I try to sample texture number 0, this is the texture that's there. Once I draw another object, I can bind another texture to the same thing. Does this make sense? So I'm binding texture number 0 to a specific texture, which has a specific texture ID, which the texture class keeps. But I'm saying I'm always going to use this basically texture, what's it called here? Yeah, active texture. And let's see, this, it has a name here. Yeah, okay. So the texture unit, basically I'm using texture unit 0, and to texture unit 0 I'm binding a specific texture. That means when I tell the shader now that I want to set the diffuse texture location to 0, I'm simply binding it to a texture unit. So if we go into the fragment shader again here, the values that are actually being sent down here in texture 2D is the UV coordinates, and here in this case I'm simply sending 0, telling OpenGL texture unit number 0 is what I want you to sample from. But behind that there's an actual binding to texture unit 0 to a particular texture. So between calls to glbind, I'll be using the texture that was bound last time to this texture unit. Does that make sense? Is this fairly clear?
Texture 2D call you're using there, is this something that's built in?
Yeah, texture 2D is built in. Texture 2D is simply a function in the shader. And what it does is it takes in UV coordinates, which are 2D coordinates, and it says these are the coordinates that I'm going to use to sample from a texture. The other number here isn't the actual texture, not the texture data, but just an identifier to a texture unit. In this case, in our case, right now, this here is just always calling 0. But that doesn't mean that it's always calling the same texture. It's calling the texture that is currently bound to the texture unit 0. But behind that, we tell OpenGL, you have a bunch of texture units, and there's some maximum number of texture units depending on OpenGL implementations. Let's just imagine we have endless texture units now. And I'm just going to say, right now I'm just using the one texture, the diffuse texture. But that doesn't mean I have to always use the same texture image. I can switch between texture images, but every time I tell OpenGL I'm going to bind this texture image to texture unit 0, then OpenGL will say, okay, now I have this pointer system here, and whenever somebody asks to sample texture unit 0, I know what image I'm supposed to sample into. But after I draw an object, I can draw a different object and say, now I'm going to bind a different texture to texture unit 0, and then the next time I'm asked to sample, I'm sampling from a different image, but I'm sampling from the same texture unit. I'm just switching between. The same as the material. You know, you can draw one object red because the values in the different material variables are different. Then you draw another object, but in between you set the variables to different values, and then you call something else. It's the same thing happening here. But the value is kind of a pointer to a place in memory where I'm storing this image. Because these images are big. I don't want to actually move these images between places in memory. These images are just loaded. So when I, here, in the create function, I call texture equals new texture this. Behind this is a bunch of OpenGL functions that will load this image, put it into memory, and get an actual handle to that place in the graphics card memory. And that image will be stored in graphics card memory, and I will have a handle to it. I'm just not going to work too much with that handle ourselves, but it's simply an integer handle. We could just as well get that handle after we load this texture, and then when we call OpenGL bind, we'd say bind this texture unit to this integer, which tells you where in memory, or basically is a handle to a specific texture. So right now I'm loading 2 textures, and so I have 2 handles. I'm only using one of them. Let's see if this becomes clearer as we move along. So the idea is here I'm loading a texture into memory. OpenGL knows where that texture is and has a handle to it. When I want to draw using that texture, yeah, we do that in Boxgraphic here. Or actually inside the shader. I say I have this texture here, and I'm going to bind that to a texture unit. I'm using a class here, but behind this would be just some OpenGL call, which is probably called OpenGL bind, or OpenGL texture bind, and it'll take the texture unit number, which I'm using here, and it'll take the actual handle to the texture in memory. But I don't want to use that data and kind of throw that around and send that into the shader. I just want OpenGL to once put that into memory and then just store it there for safekeeping. And the only values I'm throwing around are the handle to this texture and the handle to the texture unit. So when we get to the place where we actually want to get something from it, we say, OpenGL, you have some actual texture data bound to this texture unit at this moment. This is the texture unit I want you to sample from. And OpenGL will just have to know itself where to look in memory to get the actual color data for that texture unit. But here it's just an integer that's being sent down there. So the diffuse texture here is just an integer. Sampler 2D here is just a typecast for integer that has certain functionality associated with it. And this is simply a vector 2, it should be. It doesn't have to be a vector 4. We go back here, this should be a vector 2. Okay, so the UV coordinates are 2-dimensional coordinates. And make sure that, yeah, okay. But in the end, we can look at this function as a black box. We just say, I have some texture here, I have some UV coordinates, and I want a color back. And texture 2D in the shader does that for us. So I get a color back. I get the actual color that is in that pixel that I'm looking for in the texture. I multiply that with the color I get here. And yeah, and that's all I have to do inside the shader itself. So in the shader here, I set this up so that it binds it. It sets the texture, diffuse texture location to 0, because that is the texture unit that I bound it to. I could just as well do 1 here and 1 here, and it'll have the exact same effect. Just as long as I have the same 2 numbers here. So I'm saying I'm binding to this texture unit, and if I bound the texture to this texture unit, I'd better also set this diffuse texture location to that same unit. I could actually more or less skip this and just do this once in the beginning because I'm always using the same one. But let's imagine we have a more versatile system that kind of grabs these texture units from a pool. Okay, the uses texture location is just set to 1 in order to be true, here to 0, and then I set this to true just in order to be able to poll the shader for whether it has textures or not. Okay, so in box graphic, I call the shader set diffuse texture to the diffuse texture that's set in here. If I send in here null, nothing will be used. And yeah, and then I simply have to set the UV pointer here in the same way as I set the vertex pointer and normal pointers. So we have our die here. Do we feel like we understand why there's suddenly a texture on a dice there, where there wasn't before, even though we're using the vertex lighting? Okay, specular. I'm going to solid cube, yeah. So if we just put null in here, we won't be using a texture, and so we just have this white material. Okay, another thing, if we now add specularity here, specularity of 111, okay, the specularity is being added. It still looks a bit weird, but we're not kind of covering the pips as we were before, because we're calculating the entire diffuse and specular and everything in the vertex shader, and then we're multiplying the texture color with the entire thing. So these black parts here will always take the entire color down to black. If we want the specularity to kind of end up on top, we're going to need to split this and say, okay, we have something like main color, and we have specular color. So if we go here and say, well, where we simply put the V color here, we're going to have to say light 1 calculated color equals attenuation times only this. And we'll say for light 1 spec color equals attenuation times this. So I'm simply splitting the colors up in 2, and in the end I'm going to split this up in 2 as well and say V main color is basically the ambient, diffuse, emission plus light 1 calculated color, while the V underscore specular color is only the light 1 specular color. So I'm basically splitting the specular part and the diffuse and ambient parts in 2. And okay, this should work. And then I go in here and I'm going to say, yeah, main color and specular color. So I'm going to take the main color, like so. Just say plus V underscore specular color. So the texture will now not be attenuating the specular part of it. I'm going to see how that looks. Where it crashes. Okay, see that? Once the specularity affects it, you can see that the specularity is kind of overriding the pip there as well. it's kind of hard to see, but you can see it here. So the specularity is kind of coming on top of the texture rather than being underneath it. And that opens an interesting idea, and I'm not going to implement that here. It's just so much nicer to implement it in the fragment lighting shaders. So let's switch back to those. Shader here. So doing the fragment lighting. So we've implemented basically the same thing in there. You can see here how the specularity kind of overrides what's happening here. Specularity comes on top of that. And another interesting thing here, if we close this and this again and go into the fragment lighting here, you can see that obviously we're calculating all the lighting here. But before we do that, we simply set, and this is what we can do when we're doing the lighting in the fragment shader. Rather than actually kind of multiplying the texture color on top of the calculated color, we can take the texture color in first and set that to the material and then do the lighting with that material. So we're doing this first. We're saying if we're using a diffuse texture, then the material diffuse will be this. Otherwise, it'll be just whatever diffuse value we had. And in this case, I'm going to take this out again. So we're using a diffuse color from a texture, if that's an option. Otherwise, we're using it from the material specification. And we're going to do the same for the specular. So I now have the same setup for a specular texture. And I have another specular texture. And let's look at in the shader how we're doing this. Here, when I set specular texture, I do exactly the same thing as here, except I use the texture unit 1. So I make sure that I'm always using a different texture unit for the specular texture and the diffuse texture. But I still have these Boolean values to tell me, am I using it or am I not? And what we can do here is okay, so here we just have this white specularity, and you can see how it goes right on top. I'm gonna actually, this white isn't really helping that much when we have the light head on, because everything just becomes fully white. So let's just go, you can just change the texture though, right? Can we just open this with, I wonder if, no, this is all inside here. Okay, let's just go to where these textures are. Let's do two things here. Here, here. Just open dice with right. That was not what I was going to do. So let's just use a, is there a paint bucket tool or something here? We can grab some random color here, apply, override dice PNG. Well, let's keep that up there. Okay, so what I want to do is add dice PNG here, put it back in here. Let's say, okay, this is now my texture image. Okay, so I have a different color, so we can see more clearly what the specularity is doing here. So okay, the specularity is just going flatly over the entire thing. But if I want to say I want this to resemble something else, so that I want an actual texture that tells me where this object is more or less shiny or more or less reflective. Something like imagining a texture that is a texture for a wall or for a door. and that door has some drops of water on it, but it's not completely wet, so it's not completely shiny. It just has drops of water on it, and you want it to look kind of like the water drops are reflecting, but not the texture of not the dry parts of the door. But you still don't want to model that entire thing, model every single drop of water onto it, but just do it in a flat texture. In that case, we can take something like, I'm going to see what this spec text looks like right now. Come on, just in whatever. Okay, probably looks more like a star field than a wet door, but good enough. So we'll add that here and say inside here we're already loading this. Here we're loading dice, we're loading this specular texture. And so when I draw, I'm going to draw this with text here, spec text here, meaning that in box graphic it'll send something in here and something in here rather than null in both cases. And so we'll actually have textures for both of these. And inside our shader, you can see that the material diffuse will be dictated by the color in the material texture, and the specular will be dictated by the, in the diffuse texture, and this will take its color from the specular texture. So, okay, it's the same base image if we have no specularity on it. So there aren't actually those white spots in the texture, not in the color itself. But as soon as I go past and start getting some text specularity on it, is it clear on the? I get these kind of, some spots have more specularity and some spots have less specularity. So the specularity isn't happening like entirely over the entire thing.
Wait, so why isn't specularity happening like right now? What now it is?
Specularity in general isn't happening unless the light is reflecting straight into the camera. So as soon as I go a little bit out of the way, we don't see it. And because the light is following me around as well, it's only happening when I'm facing it straight on.
Oh, I see. The light is on the other side of the...
No, the light is inside me.
Right.
The light and the camera are in the same spot.
So shouldn't it reflect all the time?
No, not here, because this is facing in this direction. So if we imagine the light is inside me, it'll go into the screen here and then reflect kind of diagonally off of it. That is, if we, what is this? So the idea here being that this is the object and it has a normal that's facing here. The eye and the light are in the same location, and so the direction to the light is here, and the light would reflect to here. So if the camera was here and the light was here, then we'd get specularity here. But so the only place we're getting proper specularity is when the light and camera are straight in front of this. You just have to kind of play around with light positions. We can get this as well if we just go in here and put some other position to the light. There's just so much going on when we're editing all of this. So now I'm setting the light position to here and set it to the light that's kind of moving around in circles.
Yeah. Mm-hmm.
And of course the diffuse is also now only happening. Okay, so I have no ambience there. Well, there's some ambience, but it's very dark. So we might want to go ahead and then take the global ambience higher as well. I remember exactly where I global ambient here. But yeah, no matter. So we have a texture map on this, and now we have a specularity map as well. So the specularity Yeah, you can see now the specularity isn't happening in exactly the same time as the brightest diffuse. The brightest diffuse is when the light is head on to this. The brightest specularity is when the light would kind of reflect straight into the eye. So you can see that kind of follows afterwards. First the diffuse, then the specularity, except on that side it kind of comes before. Anyways, yes.
You've got this. You've got the shader Java file and then the shader vert and frag files. What are they for again? Like, what's the difference?
So the shader Java file is just my kind of class for communicating with the shader, for sending variables into the shader. The shader itself, the code that OpenGL reads as a shader, is the shader file. So what's necessary here is the actual shader files, the frag and vertex shaders. Those are necessary. The reason I have the shader.java is just for me to have all my communication with the shader code in one place. So what's happening here is the parts where I'm actually taking these variables in the shader and I'm setting kind of pointers to them into my code, into integer variables in my code, so that I can send data into it. So the shader file itself the shader class is just my way of kind of keeping this code contained. Because obviously if you don't start kind of making separate classes for separate functionality, your game class is going to get cluttered real fast, as mine is now, but it's all just examples and demos here. Yeah, we're kind of running out of time, so I don't think we'll have time to do a spherical map until just later in the week.
That's for spherical textures.
Yeah, spherical textures, or I mean, we can actually look at it. It's fairly quick to do now that we have everything set up here. If we look into the sphere graphic class, is it open anywhere here? Sphere graphic is here. Okay, then we're going to have to do something similar here to what we're doing here. So I'm going to start by, no, not outline sphere. Let's just throw that away, actually, in this version at least. So we'll just set the same things in here. So just going to do these same changes to this class as well. We're going to send this in here, and we're not going to be keeping this vertex pointer. We're not going to be taking that in here. We don't need that. And yeah, we can actually just take this entire thing from the box graphic, like so. We're going to need the UV buffer. We could set this up with indexing as well, but it's not necessary. UV buffer, index buffer, and then we're actually going to need to set values in the UV buffer. So we have this. We're going to need this as well. Okay, just setting up the shader. Then we can just draw this in whatever way we drew it before. We just need to make sure that we have values in our UV buffer here that are kind of correlating with the other buffers. So we have this floating point array. Okay, we might as well just make a separate array here and call it UV array.
How are you getting to the shader class in the draw function without like having an instance or something of the shader?
I'm sending an instance of the shader into it. So my main class, my main game class, has the shader, and it just tells each thing that it wants to draw what the shader is. Do you want to finish this now, or should we stop and finish it later?
Maybe we need timings.
Yeah, exactly. I think it'd be nice to just finish setting up this spherical map, and then maybe kind of being able to focus more on that spherical map and the cylindrical map and stuff like that just later in the week.